Swayam Prabha. Digital India. Educated India.
What we have discussed so far are the assumptions behind Hooke's law, namely homogeneous, isotropic, linear, elastic solid. Okay. So, under these assumptions Hooke's law is valid. We introduced material properties, namely Young's modulus, shear modulus, Poisson ratio, and then we expressed the Hooke's law in the form of strain as a function of stress, and we also saw that there are three material properties, they are dependent on each other, and we proved that only two independent material properties are there. Now, what is that we are going to do now? Express Hooke's law in the form of stress as a function of strain. So, conceptually nothing new, it just involves some mathematical rearrangement. So, let us start doing that. So, let us list down the equations for Hooke's law expressing strain in terms of stress, all the 6 equations, and then for starting the mathematical rearrangement we will sum all the normal strain epsilon xx plus epsilon yy plus epsilon zz, which means summing all the equations listed here. Okay. So, 1 by is common, and then we have sum of all the normal stresses, okay. And then we have, so I have summed up all these normal stresses. Okay. These normal stresses are nothing but the diagonal components of the stress tensor, and these strains are the normal components of the strain tensor. Okay. So, I summed up all these 3 normal stresses and then written down the other terms as such here. Okay. Now, let us simplify this, the sum of normal stresses as such as we have written in the previous line, and then I am summing up minus nu tau xx, and then I have another minus nu tau xx, that becomes minus 2 nu tau xx, similarly for tau yy and tau zz. Now, if you look at this, the sum of normal stresses tau xx plus tau yy plus tau zz is common. So, let us take that out. So, this term is common, tau xx plus tau yy plus tau zz is common. What is left out is 1 minus 2 nu. Okay. And we will write this for sum of normal stresses. The previous equation is for sum of normal strain. We will write this as an expression for sum of normal stresses. Okay. Just simple rearrangement will give this equation. Okay. These two equations, either of them or both of them, nice relationship. Why? Because they relate sum of normal stresses to the sum of normal strains, okay, or sum of these diagonal elements to the sum of these diagonal elements in terms of property E and Poisson ratio. Okay. So, that way a good relationship under these assumptions, whatever we have done, this equations, both the equations relate sum of normal stresses to sum of normal strain. That is a physical viewpoint of this equation. Okay, let us proceed further. So, now let us write down the equation for the normal strain along x direction. This we have written the normal strain in terms of the 3 normal stresses. Okay. Let us expand the equation, tau xx by E minus nu tau yy by E, and then minus nu tau zz by E, and then what I will do is I will subtract nu tau xx by E and add nu tau xx by E. Okay. So, let us simplify this. I sum up these two terms tau xx by E and nu tau xx by E. So, I get 1 plus nu by E tau xx, and then for the other terms minus nu by E is common and I get sum of the normal stresses. That is the reason in this step we subtracted and added nu tau xx by E, okay, so that we get sum of normal stresses, and we have already seen the relationship between sum of normal stresses and sum of normal strain in the previous slide, okay, which is written down here. So, that I will use this relationship here. Okay. So, on the right hand side first term as such, and then for the sum of normal stresses I substitute this expression and E cancels out, and what you have is minus nu by 1 minus 2 nu into sum of the normal strain. What we have done essentially is that in this expression we had normal strain on the left hand side, and then 3 normal stresses were present on the right hand side. We want one equation in one unknown, we want to retain only one of the normal stresses. By doing these steps in this equation there is only one normal stress present, so that we can rearrange and get an expression for normal stress. That was the idea, okay, behind all these steps. So, let us do a simple rearrangement, bringing tau xx on the left hand side, and what we get is epsilon xx plus these terms into E by 1 plus nu. Now, this sum of normal strains we can express that in terms of the gradients of displacement field. We can express as dou ux by dou x. Remember, we related normal strain to the gradients of displacement field. So, epsilon xx is dou ux by dou x, similarly dou uy by dou y and dou uz by dou z, which is divergence of the displacement field. So, let us write tau xx in a little more simpler way, E by 1 plus nu epsilon xx plus nu by 1 minus 2 nu, and then divergence of displacement field. Whenever you come across this divergence of displacement field in the future slides, it is nothing but either in terms of gradients, the sum of these gradients, or sum of these normal strains. So, we said we are going to express normal stress in terms of strains, and that is what we have done here, okay, and of course another way of representing that. Okay. What we will do now is some more rearrangement. Okay. So, what we will do is multiply with E by 1 plus nu and both the terms, okay, and then we have seen the relationship between G, E and nu, which I have derived already. So, express this E by 1 plus nu as 2G. So, tau xx is equal to 2G epsilon xx, and then put all these terms E by 1 plus nu, nu by 1 minus 2 nu as one other property lambda. Why is it a property? E, nu are properties. So, lambda is a combination of those properties. So, lambda is another property, and of course, del dot nu. Okay. So, of course, this looks much simpler, and we are going to use this form of the stress strain relationship for further discussion. Okay. Even when you later on go to Newton's law of viscosity, it looks similar to this only. Okay. Okay. So, tau xx is equal to 2 G, which is the shear modulus, and epsilon xx plus lambda del dot u. Okay. And there is a name, g and lambda are called Lamb's constants. Okay. And what we have done is normal stress in terms of normal strains. On the right hand side you have epsilon xx and del dot u has the sum of all the normal strains. So, on the right hand side you have all the normal strains, and for the case of shear strain shear stress relationship, we have seen epsilon xy is equal to tau xy by 2g. So, now it becomes very simple, just rearrange and write it for tau xy. Okay. Tau xy is equal to 2g epsilon xy. In the case of normal strain and normal stress, it involved some steps. The reason is the expression for normal strain epsilon xx, okay, epsilon xx involved all the 3 normal stresses. Okay. That is why we have to do some rearrangement and express tau xx in terms of the normal strain. But in this case epsilon, for the case of shear strain depends on the shear stress in that plane only. So, simple rearrangement is sufficient to express the shear stress in terms of shear strain. Okay. So, now let us extend, so shear stress in terms of shear strain. Okay. Now, let us extend these to other directions, that is what we have seen now. So, let us write this analogously for other directions. Okay. So, the equations written in the first line are what we have seen in the previous slide, written here for y direction, z direction, normal stresses, and shear stress in shear stress tau yz and shear stress tau zx. Okay. Just analogously we can write. And we should know that epsilon xx is the normal strain, but if you say as normal strain the purpose is not solved, because we will have to express in terms of displacement gradient, then only it is complete. So, epsilon xx is dou ux by dou x, similarly epsilon y by epsilon zz. And what about epsilon xy? It is, remember, it is gamma xy by 2, and this is gamma xy, which is the shear strain, and epsilon xy is half of the shear strain. Okay. Of course, keep emphasizing that epsilon xy is half of shear strain. Okay. Okay. Why do we express this? We do not express tau xy in terms of gamma xy, we express tau xy in terms of epsilon xy. What is the reason? Our objective is to relate components in this stress tensor to the components in the strain tensor. What is appearing in the strain tensor is epsilon xy, not gamma xy. That is why in this relationship we relate tau xy and then epsilon xy, though the actual in terms of measurement it is gamma xy. Okay. Remember, when we discussed about a linear relationship, we plotted a graph between tau xy and then gamma xy, and this slope was g. But when we want to express more formally as a stress strain relationship, we express in terms of epsilon xy. I think this should be kept in mind. Okay. Can be a cause of confusion. When we measure the difference in angle, so that is the x axis, but when express formally the component is half of that gamma xy, and that is why the relationships are between tau and then epsilon. Okay. Similarly, epsilon yz and epsilon zx. Okay. Now, to connect to what we have done earlier, we can identify that the terms written here in these two bullets, the right hand side expressions in terms of gradients, okay, all these 6 terms are nothing but the components of the strain tensor, okay, which we have discussed earlier. Okay. So, we have dou ux by dou x here, dou uy by dou y here, dou uz by dou z here. Similarly, this epsilon xy written in terms of the gradients, and similarly other terms. Okay. Now, to just to connect and then to have a recall, I have some few recall slides here. This was a strain tensor, this was the rotation tensor. Okay. Okay. What we will do now is we will connect this and recall also what I had discussed earlier. Okay. This was discussed when we discussed strain under solid mechanics. What did we do? We derived a relationship between dux, dy, duz and dx, dy, dz in two ways. First way is this, in more mathematically, which resulted in the displacement gradient tensor. The second one was more analytically, more geometrically, where we considered displacement due to a difference in displacement due to normal strain, shear strain, rotation only, and wrote these two equation. These two expressions are also relationship between dux, duy and duz and dx, dy, dz. Okay. Dx, dy, dz, these were written in a more analytical way, geometrical way. Now, based on the first equation and the second or third equation, we said that this displacement gradient tensor is equal to sum of these two tensors. Okay. That is what we discussed. The displacement gradient tensor is sum of this tensor and this tensor. What is the significance of the first tensor? That includes the normal strain and shear strain. The second tensor includes the rotation contribution, and we said this is symmetric, this is antisymmetric, and the names given were strain or deformation tensor because it involves contribution from normal strain, shear strain. Second tensor was called as rotation tensor because it involves contribution from rotation, and we concluded that translation, rotation, which are rigid body motion, and normal strain, shear strain, which are deformation, all contribute to displacement. Next, what we discussed was more importantly this particular slide. In fact, this was a concluding slide. Then what we said was rigid body motion, which is translation rotation, is not related to stress. Deformation, which is normal and shear strain, is only related to stress. Okay. Strain tensor and not displacement gradient tensor related to stress tensor. What did we say? Stress has to be related to this strain tensor, not to the displacement gradient tensor. This also is not connected to the stress. Look at the last line, relate stress tensor to displacement, not displacement, displacement gradient, not displacement gradient, but strain tensor, and that is what exactly we have done now. Okay. After several classes, we put forth the question then saying that we have to relate stress to the components of strain tensor. That is what exactly we have done in today's lecture. Related the stress, the left hand sides are all stress, right hand sides are all components of the strain tensor. So, let us look at it again. Now, it becomes very clear this slide. The what we have on the left hand side are all the components of stress tensor, okay, and as we have seen here the normal stresses and the shear stresses. On the right hand side what you have are all components of the strain tensor, components of the strain tensor alone, not the displacement gradient tensor, not the rotation tensor, only the strain tensor. And now let us look at it. For example, you have epsilon xx. What is epsilon xx? Is dou ux by dou x. What is that? This component of the strain tensor. Similarly, you have this component and this component, and then what you have epsilon xy. What is epsilon xy? This component of the strain tensor. So, whatever appears on the right hand side, these terms, and of course these terms are all, and of course we know del dot u is nothing but sum of all the normal strains. So, whatever you have on the right hand side are all components of the strain tensor. Okay. So, whatever was our objective we have achieved here, relating stress to strain, more precisely components of stress tensor to the components of strain tensor or deformation tensor. Only the normal strain, shear strain result in stresses, that is why we have done this. Okay. So, let us put them more compactly in the form of a tensor. This is the stress tensor. At this point when we introduced stress tensor, it was a very much physically meaningful quantity. We said if we give me the stress tensor, I can find out stress vector acting on any plane. Just take, do a matrix multiplication of this n vector with the stress tensor, you get stress vector acting on any plane. So, very physically meaningful quantity and useful quantity as well, but it is not measurable. It is a variable of physical interest, physical meaning. But moment we write this, as were in the previous slide, it becomes expressed in terms of measurables. All the terms here epsilon xs, epsilon xy are all in terms of the components of the strain tensor. They are all expressible in terms of displacement gradient, and hence stress tensor has been expressed in terms of measurable. Remember, that was one of the main point we started off saying, that we are going to express an immeasurable in terms of a measurable, and that is what we have done here. That is a key point here. As long as this is written, it is a nice physical quantity, very rich physical meaning as well, but it is immeasurable. Moment you express in this way, it becomes measurable. Okay. And of course, we have the property g and then lambda, they have to come from experiments, they have to come from experiment. That is why we said stress strain relationship is empirical. We cannot theoretically get g and lambda, we are only going to make some measurements and find out what is g, what is lambda. Just like to mention what is the advantage of the isotropic assumption. Okay. We said we have derived the Hooke's law for homogeneous isotropic linear elastic solid. Okay. We will keep all the assumptions. Suppose we say it is non-isotropic, what would have been the situation? Okay. We are not going to derive, just discuss that, so that we will appreciate the really significant advantage of assuming isotropic condition. Okay. Okay. Now, okay, this is the equation, of course, relating tau xx to the normal strain, tau xy to the shear strain. Similarly, let us write down the equations for the other directions as well. And of course, for the third direction as well. Now, if you look at tau xx, okay, the way in which you have derived depends only on epsilon xx, epsilon yy, epsilon zz. Okay. Similarly, if you take tau yy, tau zz, they depend only on epsilon xx, epsilon yy, epsilon zz. If you take tau xy, depends only on epsilon xy, tau yz depends only on epsilon yz. Okay. Now, what would be the more general scenario? What would be the more general scenario? Okay. What can be the general scenario? Right now, this tau xx depends only on epsilon xx, epsilon yy, epsilon zz, but in general it can depend on all these components. When I say all these components, 6 components, there are 9, but 6 are independent. So, tau xx can depend on all these 6 components. Similarly, tau xy can also depend on all these 6 components. Okay. That is what we are going to write here. So, stress tensor has 6 independent components, strain tensor has 6 independent components. So, every independent component in the stress tensor can depend on all the 6 independent components in the strain tensor. Let us write one equation for a sample. So, tau xx, suppose if we are assuming it to depend on all the 6 strain tensor components, I have epsilon xx, epsilon yy, epsilon zz. Not alone that, but also depends on epsilon xy, epsilon yz, epsilon zx. Now, look at the constants. How many constants? We have 6 constants here. Now, likewise I can write for all the 6 independent stress tensor components, which means I will have totally 36 constants or 36 properties will be there. When I say constants, remember these constants are nothing but properties, but you can prove that 15 are dependent and only 21 are independent constants. Out of 36 you can prove that 21 independent constants are there. So, if we are saying we are going to derive a stress strain relationship for a homogeneous anisotropic linear elastic material, then we would end up in 21 material properties, because in all our relationship we need to write the properties depending on direction, but moment you take isotropic condition as we have done here, we will result only in 2 constants or 2 material properties. That is the luxury I would say by assuming isotropic condition. Okay. That is why we discussed assumptions to begin with itself. The whole scope of our stress strain relationship is limited to those assumptions: homogeneous, isotropic, linear, elastic, solid.